My favorite fun fact is that you have a degree in oceanography from Scripps.
Did I hide it?
Yeah. So, Lorraine's been part of the PACE family for a very long time, really since the beginning, both as her role as the co-lead on the first two science and applications teams, but also as what effectively was the program manager for HARP 2, making sure everything was going forward. So
Yeah,
we appreciate
I'm
all
the
of that.
fixer for
Yeah,
HARP 2.
exactly. So with that, the stage is yours.
Thank you, Jeremy. Are we okay with the audio? Okay. Yeah, thank you very much for inviting me and having this opportunity to talk to you. Yes. Anyway, Jeremy introduced me, so we'll go on. I've been around a very long time, and I'm old. And because I'm old, I kind of get philosophical when I give talks now. Like, people don't remember how things were back when I started. So we're going to look a little bit in that direction. And I had to come up with a title, and I wanted to look at, you can look at it, okay, let me start from the beginning. When Ian invited me, he said, you want to come and explain something that PACE is going to do that's going to answer a specific science question. And I started laughing because I didn't think PACE was going to answer any science questions. Because it was my personal experience that you introduce new data into the system, and suddenly you realize all these things you never knew before existed, and you have a lot more questions than answers. So I went into this thinking I'm going to come in here and talk about all the new stuff we're going to suddenly discover, and our uncertainties are going to go up, and we're not going to know anything. But then I went into this talk a little bit, and I may have changed my mind. So we'll see. And I decided to look at climate change. I think that was the aerosol application I wanted to look at. You can also look at fertilization of ecosystems, which I do a lot now, or you can look at air quality, which is very important, but my interests are small in that direction. So we're going to look at climate change, and we're going to look at one specific thing. I was going to look at several questions, but you don't want me talking for the rest of the morning, so we're going to go look at one thing as we go here. And so aerosols, we're going to get some things down straight. First of all, we all know what an aerosol is. Okay, good. They perturb the climate system. And if I talk about forcing the system, that means they're artificially introduced into the system, normally by combustion of fossil fuels or human activities here and there. So forcing means human activity. And the way forcing is used in a climate construct, it means you run a climate model and you use the emissions from pre-industrial times, and you run it, and then you run it with the modern emissions, and you see the difference. That's all climate change means to a climate person, and they're all modelers, all of them. They don't know what to do with real data. Meanwhile, you can also modify the system even if they're part of the natural system. Like, there's always been aerosol, right? There's lightning strikes, and there's burning and smoke. There's dust that comes naturally from wind. All this is natural. And the climate modelers don't care about anything that's natural in the system, even though I happen to think that's still interesting. We know that a direct perturbation means that the aerosol is interacting radiatively in the system and changing the radiative balance directly. An indirect perturbation means we modify clouds with the aerosol, and then that in turn affects the Earth's radiative balance. So we're all clear here, right? We're all starting at the same place. I'm going to show you a series of bar charts. This is the first one that I'm aware of. This is from Hansen's paper in 1981. That was my first year of graduate school at Scripps. Okay? Raise your hand if you were alive in 1981. Yeah, see, that's what I'm afraid of. So, and by the way, I want you all to know I flunked out of Scripps. Flunked out, told to leave. So, came back later. Your graduate career could be very interesting. Hansen was looking at the change in temperature from different forcing components. And he has a lot of different types of things. And the aerosols are kind of like in here, and a warming is black, a cooling is white. So he has two aerosol competing components here. He's got forcing from the input a sulfate aerosol. Sulfate is a white aerosol. It doesn't absorb any radiation, and it reflects more sunlight to space. So you put a bunch of sulfate aerosol in the atmosphere, and the sunlight kind of gets reflected back to space, and that cools the planet. So we're all good with this, right? You add more aerosol, more white aerosol, it's more reflective, the planet cools. That's white. Meanwhile, the same processes that are inputting sulfate aerosol into the atmosphere, they're inputting what he's calling soot. It's an aerosol that absorbs light. So now here comes the sunlight into the system. It goes in the aerosol, gets absorbed by that aerosol, it stays in the system, and things warm up. Okay, so we have cooling, we have warming. They're both aerosol factors, and they're competing with each other. 1981, this is what the picture was. We're going to move ahead a ways. This is 1995. This is the second IPCC report. This is when all the climate people get together, and they talk about what's real, they try to get a consensus report of what they understand. And now we're starting to talk about aerosol forcing, and we're looking at it in terms of watts per meter squared now. No longer change in temperature, because that's another step of unknowns. This is the actual forcing, the human impact on the climate system through inputs of different components. And each component is impact with a guess of what it's going to be and an uncertainty of how well we understand it. And in this, we have our sulfate aerosols, we have our soot, and we've added biomass burning because suddenly between 1981 and 1995, they realized that people were doing agricultural burning. So all those European and American scientists never understood that the global south was burning things intentionally, and it was inputting a lot of aerosol to the atmosphere. And what I'm going to be looking at here is not the guesses of the forcing itself, but how well we understand that, the uncertainties, the error bars. And what from this chart, reading it off the chart, I got, these are the forcings in watt per meter squared, 0.5, 0.3, biomass burning is 0.65. And then there was this thing here that no one was even about to make a guess of what happened when aerosols affect clouds and how that would change clouds and how that would create a forcing. No one's even willing to guess. They just said, we don't know. And they guessed we don't know in terms of 1.6 watts per meter squared. So suddenly aerosols have become really important, and especially because of its effect with clouds, the indirect. Okay, next IPCC report. We got color. And as we go through here, I'm going to be putting the new ones in a different color as we move forward. Well, we decided that we didn't know indirect effect even more. So it wasn't 1.6, it was really 2 watts per meter squared. We didn't know what indirect effect was. And everybody else grew. We added mineral dust because suddenly there was a few papers out in this time period that said people are disturbing the surface of the desert and they're creating more dust because we're disturbing ancient soils. But we don't know if that's going to be warming or cooling. I'll just throw those error bars in. So if you look here now, I've added the uncertainties in blue. There seems to be slight improvements in the sulfate, in the soot. But mostly more and more unknowns. Like the more we go forward, the more we look at the problem, the more we don't understand it. Okay? Shall we move ahead to our next IPCC report, 2007? All right. They gave up now in trying to distinguish between the different components of the aerosol. And they just said, this is all the direct effect. We're going to put it in one place. This is all the indirect effect. The indirect effect is starting to get guesses on the magnitude and the uncertainty. And the uncertainty has gone down from 2 to 1.5 in the indirect effect. And the total uncertainty went down a lot also at this point. People were more and more confident. Let's move ahead. 2014. Well, where are we now? Well, first of all, they put the components back in because whoever was writing the report decided we really need to see the components. But they put it in one bar, so it was compromised. And the soot factor, the absorption factor, was still pretty big then. And the uncertainty on the indirect effect went down a little bit. So we are moving along. And then our most recent IPCC is this one. This is 2021. And it's the direct effect doesn't seem to budge, right? We still have this uncertainty all the time with the direct effect. And really, not much has changed in terms of our understanding of climate change from an aerosol perspective in this consensus report from the 5th to the 6th assessment. Kind of stagnated. And don't tell me no one's been looking at it, right? People continue to work and work and work on it. We've made a lot of improvements in models. The models have jumped way ahead, right, in what they can do. But they're running unconstrained. They're running, they run and who knows if they're right or not. They're unconstrained. But let's look at this all together as a time series from 1995 on the right to 2021 on the left. And this is the total aerosol uncertainty, and I calculate this by combining the components in a root mean square kind of fashion. The biggest improvement in our understanding of aerosol effects on climate change happened between 2001 and 2007. Okay, for a while things were getting bigger. We don't know, we don't know, we don't know. But something happened before that 2007 report that gave people the confidence to decrease the uncertainty and the error bars on these estimates. What happened? It was the dawn of the satellite era, the modern satellite era. This is when the EOS satellite sensors went up. MODIS, which is the one I worked on. MISR from JPL. OMI and Calliope, which is the LiDAR. These were not active sensors, but these were workhorse sensors in space that were returning terabytes of data that people were able to use, and they were using it extremely creatively to get answers. And this image I have here in the lower left comes from a movie that we made of the entire 2001 year. It's daily data with a Gaussian over it. So it's like it's a running average of about 11 days to create these images. And it showed what we could do from the MODIS satellite. And the reason we did this Gaussian and this running average like this so that we can see through the clouds, because on any given day, there's holes all over because of places we can't retrieve. And the thing with MODIS was not just that we can get aerosol optical depth, and let's find out, does anyone know what aerosol optical depth is? You got to know what aerosol optical depth is. No, you guys don't. All right. You do. You don't. Do you know how to raise your hand? It works like this, okay? Aerosol optical depth is a measure of how much aerosol there is from an optical perspective. It is the integration through the column of the total extinction of light by the particles. So it tells you if there's a lot of extinction of light, there are a lot of particles there. If it's clean, then there's not much extinction. So aerosol optical depth is a measure of how much aerosol there is, but not by concentration, but by its optical properties, it's light extinction, okay? So a picture like this of data, not model, you could see this from models all the time, but data, that measurements, came from measurements, showing where and how much aerosol was distributed across the globe was mind-bending to the people who saw it in the early 2000s. And it was over land and ocean. There had been satellite products before, but they were only over ocean, and they had their problems. But this was over land and ocean, and we could see the hot spots of where the aerosol is. We could see the aerosol in this June image of the dust crossing the Atlantic. We could see the East Asian plume at the time in the early 2000s when before China had put in their pollution controls. We could see it. We could see the aerosol over Europe before Europe. This was just amazing to see all of this. And if you run the movie and you can see it changing over the course of the years and the season, over the course of the days and the seasons, it was really remarkable. The other thing that we could see that no one had seen before from space is that we have a double color bar, so that we have what we call fine mode fraction or small fraction that was red. So if the particles were small, it would be red. If the particles were big, it would be green. And as we move from blue to a more intensity, you would get more loading. So not only could we see where the aerosol was and how much, and quantitatively how much from an optical sense, we could see if they were large particles or small particles. And that leads to understanding what type of aerosol was there. So the kind of this greenish stuff is large particles, which makes it dust, desert dust. And desert dust has its own set of optical properties and ways of computing its forcing. And the red stuff was carbonaceous aerosol, or aerosol, not necessarily carbonaceous, but aerosol from combustion. So it could either be smoke or it could be pollution, sulfate pollution. And so doing this, we constrain the climate models. We could tell the climate models if they run and they get a picture that doesn't look like this, that they're wrong. And they would have to go back and fix it and run it again. And we can constrain the climate models in terms of their loading and the aerosol type. Okay, so suddenly all the climate models started to agree when it came to aerosol forcing, because they couldn't run make a run that didn't look like this picture. And so suddenly they all agreed. And if you dug down into it, they all agreed for different reasons. So if you looked at how much dust, or if you looked at deeper than the aerosol optical depth, they didn't agree still, but they were constrained to get the right answer because they knew what they had to get to. Okay, so we understand what the EOS satellites brought to the climate question is this ironclad, you have to get this picture. Good? We're still good? Okay. So let's look a little bit. This is Jeremy's picture of the two dust things that I use over and over again. It's the best picture ever. The one on the left is smoke fire from Portugal fires, smoke image from Portugal fires. And the one on the right is dust from Northern Africa. And you can see the aerosol. Do you see the aerosol that comes out over the ocean and over the clouds? Okay, let's look at that one first. When that aerosol is over the ocean, over the blue ocean, and you had dark blue ocean, and now you put an aerosol on top, what does that do to the radiative balance at top of atmosphere? Are we warming or cooling when the aerosol goes over the ocean? Okay, is the scene darker or brighter than it was before? It's brighter than it was before. That means more radiation is going out to space because we're seeing more radiation. It's brighter. But when that aerosol goes over the clouds, it's darker and it's warming. It's creating a warming. So if we're trying to do this from MODIS, we'll never see the aerosol that went over that cloud. We lose it. So we don't know, we don't catch the warming part of the equation. We only catch the cooling part. And if you look at the mineral aerosol that's coming off of northern Africa here, we don't see it going above the cloud, we see it going below the cloud. So when we lose it in those clouds, it doesn't matter because the clouds are clouds, right? But we don't know that from MODIS. We only know we lost it. So we can't conjecture that this aerosol plume has gone over the clouds and therefore it's going to change the radiative balance on top of the clouds. We just don't know. And we don't know from the Portugal side either. So we've lost it. The other really clear thing we see here, the two mineral aerosols have two different colors. So the bright one is going to have a very different effect on radiation top of the atmosphere than the dark one. The dark one's absorbing light, it's holding on to the light, it's reflecting less. So they're going to have two different effects at top of atmosphere, and that has to do with their absorption properties. So we see from this picture, and I'm going to tell you right now that MODIS wouldn't be able to distinguish between those two. It would just say dust aerosol, big particles. It's going to have these optical properties, and it'll look like this in the forcing. So we can't tell. So this is what's contributing to the uncertainties now that haven't budged since 2007. And if we had to make a wish list to reducing those estimates of uncertainty, we always have to know how much and where, and the global distribution of aerosol optical depth, which we have now beautifully. We need to know how much is backscattered to space. These are the optical properties and the phase function, the angular distribution of its scattering. And we can sort of get it because we can get aerosol type to a degree, so that's why it's orange. But we also know how much is absorbed in the atmosphere. Are we working with bright dust or dark dust? And these are the optical properties, which is the absorption, and we're going to use a term called single scattering albedo to talk about absorption. We need to know how much is above clouds, and is it above clouds, the aerosol layer height, and how much of it is above clouds, and what's going on up there. And because the indirect path of aerosol affecting clouds is so important, we need to know what are the cloud properties with and without the aerosol present. And that's a very important piece. It's going to reduce uncertainties. I'm now going to, we don't need that. Let's just talk about PACE. Now, you know PACE has 3 instruments. I'm going to say right now, all 3 PACE instruments are excellent for remote sensing of aerosol. It's not like the polarimeters do aerosol and OCI does ocean. No, 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 no. OCI is a wonderful instrument for aerosol. And this is, we'll start with the ocean color instrument. This is work with a team that I've led now for, I don't know, a long time, almost a decade. We're done. Our funding was ended, but we're done, but we've been able to finish and deliver a product. This OCI is the first NASA opportunity to measure UV channels at 1 kilometer resolution. There have been UV instruments before, but they have these huge footprints. It's the first truly broad spectrum instrument across the solar spectrum. And I want to emphasize solar spectrum. It doesn't have the thermal infrared channels. And once you start talking about clouds, That's a big loss. If you're the cloud group, it's a big loss. And the reason it's so important to have this broad spectrum for aerosols, the UV is sensitive to aerosol absorption and layer height. The visible to the near infrared is sensitive to the aerosol loading. That's why we could get AOD from MODIS. And then sensitive to aerosol size, you have to go out to the shortwave infrared. That's why we had red and green colors on that map, because we went out to the shortwave infrared with MODIS, and we could get the size. So you understand this? We've never been able to put this all together on one instrument before. This is the algorithm that we built. I'm very proud of this flowchart. You can read it another time. But the idea is that we unified 3 heritage algorithms, deep blue and dark target from the MODIS-VIIRS kind of history, the near UV from OMI, TROP-OMI, and EPIC. And this is what we're outputting. We're outputting AOD across a broad spectrum. We're outputting the aerosol above the clouds now, never done before, where there's single scattering albedo in 3 to 5 wavelengths. That's the absorption of the particles, bright dust or dark dust. UVAI, that's UV aerosol index at 1 kilometer, never been done before at that kind of resolution. We're doing the fine mode fraction over ocean like we've always done, and aerosol layer height from 2 independent methods. This is UV aerosol index at 1 kilometer, showing you on the left. That's what we're doing now for OCI. This is smoke plume over northern Canada. On the right, I pulled from Worldview. This is what we can get from OMI now. OMI has a 13 by 24 kilometer resolution. Got it, guys? 13 by 24 kilometers. And that's the kind of image you get. Meanwhile, what we have is this very nice detailed image of the smoke plume. And this is, you can see here, this is where OMI gets it okay, but then it kind of goes around, and that's what we can see from the UVI. This is our AOD product. This on the left, clear sky AOD, it's all you've ever seen from any instrument up to now. Everybody, right? Aerosols in clear sky. But now we're retrieving aerosol above cloud when the aerosol is significant. We can't do it when it's just tenuous. But when the aerosol is significant, when it's going to count toward climate change, we can do it now. And we can put it together and create this all-sky AOD and fill in the hole. You see there's a hole here that we've never seen before. This is a smoke case. It's very hard to see from where you are, but there's little dots on here. Those are the, using the same color bar, the AeroNet coincidence for single scattering albedo. We have 2 different algorithms running right now to do this single scattering albedo. We're in the process of evaluating which one we want to go with, right? And at this level, they look very much the same. The dark target one only works over ocean, not land. That's why there's difference. But over ocean, where they're both retrieving, they're pretty close. When you look at them on a monthly mean, they're no longer that close. And so we'll talk about that. This is the aerosol layer height from what we call the near UV retrieval of the aerosol layer height. It's a little bit messy. I'd like it to be a little bit less variable on the short scale, but when we make the monthly mean, everything kind of falls into place. We have to look at it some more. We're also deriving aerosol layer height from an oxygen band retrieval. It's in the latest version, the last version that we gave to SDS to process, but I have no examples of it now because it was not processed at the same time as everything else. It was the last edition. This is the monthly mean AOD, showing both the above cloud and the clear sky, I believe. This is the single scattering albedo from the two different methods. The near UV SSA is showing a much darker Earth in terms of aerosol, much more absorbing aerosol than the dark target that only works over oceans. We have reason to believe now that the near UV picture of the world is the more accurate one, but it's still under evaluation. I think the indication is that the aerosol is darker than we at first expected. So this would be a new finding from PACE once we can feel comfortable with this. This is the validation for the near UV single scattering albedo. We get 67% of retrievals, one standard deviation of retrievals within plus or minus 0.04. That is our uncertainty. So we put error bounds already on this retrieval. And this is the aerosol layer height. I told you by the time we get to the monthly mean, the height's starting to make sense. Though smoke in Canada went up way high, right? Hit the tropopause, way high. Who knows what a tropopause is? Okay, that's very interesting. I'm always worried about these things sometimes when I'm talking to mixed groups. The tropopause is the place when, if you go up in the atmosphere, it gets colder and colder and colder and colder, and then you hit a certain point where it starts getting warmer. The tropopause is that bend in the temperature curve, and it's kind of where the lid is. All the stuff that happens in terms of weather and everything always happens below that point. So when an aerosol goes up that high, it's really hitting the ceiling, and sometimes it penetrates. It's got its interest. And just for good completeness, that's the UV aerosol index and the fine mode fraction, which are working just as expected from heritage. Okay, we're going to put OCI aside, and we're going to add a few slides and look what the polarimeters offer. Are you guys bored? Because at the end, we're going to go back and look at whether we're going to actually make a change in the uncertainties or not. Okay? So don't go away. And polarimetry is very new to space. These are all the Earth science missions from the beginning of time, 1960, all the way to now. There have only been 3 polarimeters in space. It's a new technology. Until UMBC, here, right across the hall, we built a HARP CubeSat. You know what a CubeSat? They're tiny little things, right? And
I brought it yesterday.
You brought it? You brought it? Okay, so you built that too, right? You were here? Yeah. Okay. Yeah, you disappeared for a few years. I can't remember. So it was this little thing. And so that was launched here. That was the first time we'd had a polarimeter in space since there. And it was the first time the US had launched a polarimeter in space. It was our first US polarimeter. This tiny thing, you know, you'd think the US would put some more interest in it. And then after that, we have HARP 2 and SPEX 1. Okay, so I just wanted to tell you how rare these things are. This is imagery that Anand gave to me to show here. I don't know who made them. I hope it was him, but it may have been Brent. It may have been Richard. I just don't know. This is a case of forest fire smoke, and what Anand has chosen to show here is it's not forest fire smoke. It's biomass burning in South American Amazon, and it goes. It gets burnt in the Amazon, and then it goes and it hits the Andes. See, so this is the Andes here, and the Altiplano, and here's the Pacific Ocean and that curve of South America. You got your guys oriented now? So it gets burnt, and it doesn't go over the Andes. It kind of goes down the side of the Andes. That's what we're seeing. You're showing the AOD because you have to show that because everyone expects it. But what they can also do with this polarimeter that I have not yet done and may never have a chance to is break it into components between the fine mode and the coarse mode. How much AOD is produced by small particles versus large particles, and all the smoke is fine particles. Yes. Okay, he's got an angstrom exponent, which I never produce or show, because I don't believe it. And then there's a single scattering albedo, which is very important here. And he's showing it very high, saying that this smoke is a very bright smoke. It doesn't absorb very much. It's a white smoke. And it kind of looks whitish there. So that's the smoke case. Here's the same thing for what he's calling pollution over India. This time the smoke is up against the Himalayas in north of India. The AOD, fine mode, coarse mode. There's almost no coarse mode. This is a pollution. It's a fine mode particle. It's made by combustion. The angstrom exponent and the single scattering albedo, again, this is a white aerosol. It's not very absorbing. This is their dust case off the coast of Africa. AOD, AOT. Now all the AOD is bright in the coarse mode because these are big particles. And the single scattering albedo shows some absorption at 550, a little bit. So this is a little bit more absorbing than the very bright aerosols that he showed earlier. They have put it together into a big global picture showing different aerosol in different places. This is the AOD. They're still working on things, but it looks very pretty. There's another algorithm. This is all done using GRASP, which is the algorithm that is being used at UMBC. This is something that Mengal gave me. And this is using it's applied to HARP too, but it's a different algorithm. It's called fast maypole. It's only being applied over oceans. And he's showing aerosol optical depth, fine mode volume, which is like my fine mode fraction, and the single scattering albedo when there's enough aerosol to make it possible. You have to have some signal to do these other things. So that's again, it's a very pretty picture here in the global sense. This is another Mengal fast maypole showing the different quantities from the fires in Los Angeles in January that produced smoke that went out over the ocean, and he's capturing it here. At the same time, there was a dust plume coming out from Baja California. So you can see the difference in fine mode fraction. The reddish in the middle of the image is small particles. The bluish is the large particles from the dust, and how they have different absorption properties as they came out. Okay, one instrument, two algorithms. We can handle that, right? All right, and specs one. This I got from a published paper, which I find amazing that they have a published paper already and we have nothing. What they chose to show is the AOD, because you have to. They do angstrom exponent, which is a mistake. And their single scattering albedo now is beautiful. It's a 6-month mean. Because specs is such a narrow swath, it takes a long time to build up statistics to get a picture like this. But again, you're seeing the distribution of the absorption properties of the aerosol over the globe. When these things start getting out and start getting some publicity, people are going to go, wow, the modelers are going to go home and start screaming because they have to match this now. And yeah, it's interesting. This is their validation. This is Specs 1's validation against AeroNet. Okay, that's a better one. Raise your hands if you know what AeroNet is. Okay, good. Okay. You never know, Brent. This is the validation of their quantities. I only put the numbers, the fuzzy numbers you can't read, but the numbers I was interested in were the single scattering albedo. They separate land and ocean. They're doing very, very well with this. If you want to compare it to what my group did, it's not that much different. So it may be a little bit different, but I don't know everything they did to get it. And so The question is, do you need polarimetry to get the single scattering albedo or not? It's a question. Okay, so let's go through this one more time. One radiometer, OCI, 2 algorithms. I only showed the UAA. There's another algorithm on OCI that's very separate from us. It comes, what's the name of their algorithm? Jeremy, what's the name of their algorithm? No, it's for OCI. OCI. Yeah, it's Alexi's algorithm. MAYAC, yeah, thank you. There's another algorithm on OCI called MAYAC, and we've developed it completely independently. I know nothing about what they're doing. I know nothing about their results. My guess it's going to be very good because the MAYAC applied to the heritage algorithms was very good. So that's all I can say. There's 2 polarimeters. HARP has 2 algorithms. SPEX1 has 1 algorithm and a published paper. New to PACE, spectral single scattering albedo, the absorption, AOD in fine and coarse modes separately, aerosol layer height, and AOD above clouds. Is this enough to reduce the uncertainties in the climate problem? And the answer is maybe. Like I said, before we started, I was going to say no. All right? But this changed my mind a little bit, that there was a huge drop in uncertainty once the EO satellites came there. But we need more characterization of particle properties than type to go any further. And we may have it, right? So we looked at this, and we may have it, and we made a wish list. And now what's PACE going to do here? Well, it's turned 3 and 4 green. We can get the stuff above clouds now when it's important. We can really get to the absorption in a way that we've never gotten before. And I don't know how to characterize 5 because it's interesting, but people have to be thinking about the aerosols and clouds together to get it to work. So the answer is maybe. And it depends on how well the instruments perform over the long term. They're doing really well now, but we have to get a lot of data to really make a difference. How accurate the algorithms for both aerosols and clouds turn out to be. What is the uncertainty on the retrievable single scattering albedo? And is it enough to constrain the climate models to the point that they move forward? And then how creatively users manipulate the data. It's very easy to do data now, but there's a knack to taking data and pulling signal out of it, right? So it's the creativity that you take to the data that's going to make the difference. And how aerosol and cloud products are used together. Because the biggest uncertainty is how the aerosols affect the clouds and how that comes back to climate. And that's kind of where I'm going to leave you. With a maybe. Sorry about that. But it's better than I thought when I started. Okay? Can I take questions? Yeah. What?
Mic for the recording.
Okay.
Thanks for your presentation. I really love it about all the multi-instrument and the comparisons. You mentioned a few times about angstrom exponent and how doubtful you are. So I was working on angstrom exponent comparison with modeling data, and I'm halfway through, like for my work, of course. And now I was wondering if you could elaborate more on that. And I have a second question. If we're about to simulating satellite products, such as from PACE, we usually only do AOD. So what would be your recommendation to look at? Because it's funny, the second things we were thinking to simulate was actually using angstrom exponent. There were a few papers on it, which I was also in doubt on the quality. So what would be the option instead of angstrom exponent like SSA or maybe something fancier or something simpler. I don't know.
Okay, so whatever you're doing now with angstrom exponent is perfectly legitimate, okay? Just because I have a pet peeve doesn't mean the community's behind me. What wavelengths are you defining your angstrom exponent for?
Well, we're considering two 440, 670, and the 440 with a longer wavelength, like 1067.
Okay. They're different, right? Yeah. Because, I mean, I love to draw here, but we can talk a little bit later. When you plot the spectral AOD on a log-log plot, right, spectral AOD on log-log plot, angstrom exponent assumes a straight line. Yeah. It's never, ever a straight line. It curves, yeah. Okay? And that curvature is very important. It goes one way, it goes the other way. So by doing two different angstrom exponents like you're doing, you're trying to get to that. You're trying to bound that somehow. But every time you choose two different wavelengths, it's going to be different. So people are always comparing this angstrom exponent to that one, to this one, and they're all completely different values because they're all defined by different wavelengths. Okay? And what angstrom exponent is getting you is a feeling for the aerosol size of the particle and its phase function. My preference is to use a spectral AOD to define fine mode fraction, which is what we've been producing from MODIS, and other people have similar things like the fine volume from Specs 1. That is a, who did the fine volume? Brent left. Okay. That was you, right? So that's what Fast Maple's doing fine volume, which to me is a better measure than angstrom exponent. But I said, whatever you're doing, it's okay. No one's going to tell you you're doing it wrong. Single scattering albedo is a completely different animal. It's absorption, it's not size. And I think it's a more important parameter, but size is, they're equally important. So I wouldn't switch in midstream. I would just be very aware of the limitations of what you're doing in terms of what a real spectral dependence looks like. Okay?
Thank you.
Any other questions? Kirk, and Claire. Kirk, do you mind if I do Claire first so I don't have to walk back and forth?
Hi, yeah. Thank you so much. That was a really interesting talk. I probably could ask you 500 questions.
Okay.
Just stick to one for now. Let's see. Oh my gosh, I totally blanked on what I was going to say. Okay, yeah. For the radiative forcing, there's two bits that go into it. And so you're showing these bar charts that are estimating the radiative forcing since 1750. Mm-hmm. So we have to understand the radiative impact of aerosols, of like a unit of aerosol. That's part of it. But we also have to understand what the change in the amount of aerosol is since 1750.
Yes.
And that's kind of always, to me, the elephant in the room when I look at those IPCC figures, because we certainly didn't measure anything close to that. We have no idea. For CO2, that forcing, we do have a pretty good way of measuring CO2 since 1750, so we can constrain how much it's changed. But for the aerosol, we don't. So there's the part that you've been talking about, which is kind of like what is actually the radiative response to adding or removing
but we have
some
no idea.
aerosol, and that's unknown. But also just how the aerosol has evolved over time.
We have no idea.
What is? do you have a sense of like what is the relative amount that each of those are contributing to that uncertainty, and any creative ways that we can go about understanding what the aerosol loading might have been in 1750, both from the
I have a very creative
and
way. A long time ago, I wrote a proposal for fun about building a time machine and going back with instruments to measure the aerosol in 1750. I could share that with you.
There's no deposition record that you could look at? No.
No, it's globally.
Well, not globally.
Well, globally, climate's a global problem. So, you know, they're making guesses based on industrial outputs and population. You know, I don't know. I do know that the climate models have no hope until they can match the parameters that we see now. Okay, so that's the constraint. But you're right, who knows? But don't tell that to modelers, you know,
I am a modeler.
you are a modeler. They really believe their models usually.
We don't believe our models.
Good.
The
I
hidden
don't
secret
know.
is that modelers don't believe our models as much as observationalists don't believe their angstrom
Yeah, we
exponents.
don't believe our. I don't know what to tell you. I mean, it is going to be an uncertainty. How much of that uncertainty shows up in the bar charts, I don't know. But, you know, I feel that the uncertainty in the bar charts are really made from a diversity of model results that as soon as the models start to agree with each other, the uncertainty is going down.
Well, the interesting thing about the models is they all use the same prescribed forcings time series, and so it's not going to capture the uncertainty in what the
No.
emissions were.
No, it's not. I don't know what to tell you.
Yeah.
I would love to go
Okay,
back
we'll
and
talk
see
about
it.
it later.
Yeah, I would like to go back and see it. Yeah.
I lack familiarity with how the models sort of operate, but in that bar chart, I saw the different forcing mechanisms kind of separated into like distinct columns. I would imagine, like in the ocean, there's interaction between those, like sulfate and soot. If you have more scattering elements, that's also more chances for it to be scattered into the absorbing component. Are those things sort of combined and those interactions considered in models, or are they sort of treated as independent, distinct things that never really interact with one another?
I think there's a lot of interaction now. The chemistry is pretty advanced. I don't know.
If you're asking how it's actually treated in the model, then the interactions are all there. If you're asking how it's separated to plot in that bar chart, then that's a slightly more nuanced question. So models run what we call like single forcing experiments, where we only change one of the forcing components at a time. So like we'll run a simulation where we just have CO2 but no change in aerosol, or just change the ozone and no change in anything else. And that's kind of how those are often constructed. But we, on the whole, don't run, aside from a handful of people, don't run experiments where we have different types of aerosol perturbed separately. But some people are really interested in that.
Yeah.
Thank you. Great.
Someone at the back table?
Oh, Kirk, I know. I'm on this side of the room, so.
Hi, Raman. This is Piyush. I'm from Esron. Thank you for the very informative talk. So my question is about the difference between that SSA, what you found between the two algorithms like NUV and the OCI. So I'm very curious to understand that how that understanding has developed, that now we have to consider aerosol more absorbing. Because as I know, as per my understanding, that the previous satellite who has given the SSA, and they have a very nice match with the Aeronet SSA. But now, like, we also compared with the specs one with the Aeronet, and we found like a lot of diverts. But yeah, I'm really curious to know about that, how that understanding has developed, that now we have to consider the aerosol more absorbing, and how that will affect those IPCC reports, that maybe coming reports.
First, we have to be confident that it's right. Okay, this is new. It's hard to validate SSA because it takes an inversion on the ground to match the inversion from space. And most of our sites that can have instrumentation that can do that are on continents. So you're always skewed toward understanding the single scattering albedo from continents. And there's an uncertainty in that part of AeroNet that's comparable to what we can do from space. So you've got error bars in both directions. So it's a little wishy-washy. I would not go out proclaiming that the world is darker until we can actually, we're very comfortable with that. I know why the two algorithms don't match. I know that, which I can communicate. And we have cause to believe that the darker one is more accurate from just spot checking where we can. But it's still spot checking. We know why the near UV has such sharp ocean continental contrast, and that is traced back to the information that we send to it from the overland retrieval. We constrain its retrieval single scattering albedo from the AOD that's measured from the dark target in deep blue. And there's some issues in feeding that information over the African continent based on our needing to nudge the model that's used over the African continent. That's not accurate. So rather than the oceans getting brighter, I think the African continent is going to get a little darker to start with. It will have, I think it will have implications in terms of modeling climate change, if we're comfortable with it. But right now, I'm not, I would not run out and say that the world is darker. I think there's a potential for it.
I think, or Mung.
Well,
I think Kirk first.
Kirk first.
And we're wrapping up after Mung.
I just wanted to say that I agree with you about angstrom exponent. And for other reasons too. It's very a challenging parameter numerically.
It's so last century.
Right. Yes. But here's our fundamental problem, is that the parameters that we are retrieving from all of the algorithms are optical parameters. And the parameters that are going into the climate models are chemical and physical parameters. They're not the same thing. And so, we've had the luxury of the previous generation of instruments to really work on the best ways of relating those two data sets. And the challenge we have now is how we can do that properly given these new data sets.
Yeah.
Arlinda da Silva, who used to work at the Global Modeling and Simulation Office at Goddard, would regularly say to me, there's nothing I can do with the polymeters on PACE. There's no useful information to me. And mostly he's just trying to irritate me.
Yeah.
But what he means is he doesn't know how to use the parameters that we're measuring. And I think angstrom exponent and AOD are useful because that's what's been used already, and we need to connect to the prior versions, but we also need to be thinking about how the other parameters that we're retrieving, what is the best scheme of things? And I don't know how to do that. It's one of my sort of heartburns, but hopefully as a community we can figure this out over the next couple of years. I did want to say one other thing. You had a list of polar emitters that are in space, and there's not many. But 6 days from now, another one is due to be launched.
Yes.
UMetSat is launching, I guess it's METUP SG-A1, which has the 3MI instrument, and that's a successor to the Polder, the French instrument, several generations of that. It's an extension of it that has SWIR channels. So we'll have another polar emitter in space soon as well.
That's good.
Anyway, should I take it to Mung?
Thank you, Lauren, with a nice talk and nice history. Actually, I'm born in 1981. Now I feel, I have some responsibility. So my question actually is, you have a summary, right? Over the last 10 years, the aerosol uncertainty is reduced from 1.62 to 1.6. I think for someone who is not in that field, they may feel we don't really do much things, right? And so my question is whether there should be another metrics to measure our confidence level on the uncertainty, like the uncertainty or uncertainty, or maybe before we don't know how much we don't know, now we know how much we don't know, kind of thing, which can be a better way to deliver, from not just the instrument uncertainty, but also, the knowledge we have accumulated. Maybe another philosophical question, right?
What did you say? I don't know how to answer you, Meng. You keep hoping the uncertainties reduce, but as Claire says, we don't know what, the way they run the models, we don't know their starting point. Yeah, I don't know how to answer you. This is the first time I've ever looked at the uncertainty as a function of time, right? To see the changes and to see that the last 3 reports, nothing changed. I thought that was interesting. And people have been working, right? Yeah. Yeah, I don't have an answer, and maybe it's what Claire says, is that we don't know what pre-industrial aerosols look like. I don't know. I'm hopeful that the type of measurements we're making now from PACE will help do what Kirk needs to do, or said to do, which is turn the optical into mass and concentration better, because we're doing more than constraining type. We've got more measurements there. But this all has to be done. Yeah. Anyway, thank you.